Hello, students. In this video, we're going to discuss enthalpy and, most importantly, how we can use the enthalpies of reaction to do stoichiometric calculations where we can determine the amount of heat either released or absorbed in a balanced chemical equation. So the enthalpy of a system is the sum of the internal energy of the system and the product of pressure and volume. So we can basically say that enthalpy is H equals energy plus pressure and volume. And enthalpy is a state function, which basically means that we are only concerned with its final and initial states and not the path of getting there. The enthalpy change, delta H, of a reaction is the heat evolved in a reaction at constant pressure. So you can think of an enthalpy of reaction as really Q of a reaction at constant pressure. What I always tell students is these are really the same thing. It's just at constant pressure, we call heat enthalpy. So you can think of enthalpy as Q at constant pressure. And typically when we conduct our reactions, the atmospheric pressure or the external pressure is constant, right? If I neutralize an acid and a base, two solutions, combine them, the external pressure in the lab is going to be the same. So it's constant pressure. So that heat that's being released in that neutralization reaction is really the enthalpy of the reaction. So that's just another name for it. So don't get too wrapped up with that. And usually the enthalpy of the reaction or the change in enthalpy is similar in value to the energy. And that's because if we recall, energy equals Q plus W, right? And if we replace energy could equal enthalpy minus P delta V. And we can also see if I add P delta V to both sides, that's just this reaction up here, or that equation. But the whole point of most of the reactions we observe in lab, there aren't a lot of volume changes, right? In a lot of the solution chemistry, there isn't a large amount of, it's negligible. So there isn't a huge gas production. So in that case, a lot of times these values are very close. Now, in the cases where there are a large amount of gases produced, then they're not going to be quite as similar. But for the most part, your enthalpy is a really good way of measuring the amount of energy released or absorbed. So in endothermic and exothermic reactions, we have to incorporate the unit of energy, joules or kilojoules, and we have to know where it's coming from. So if it's an exothermic reaction, we know that heat's being released. And again, enthalpy is just heat at constant pressure. So my enthalpy is negative. So sometimes you'll see it where they might just write out the balance equation with the reactants and the products, and they'll just show that the heat is being released. So they'll write it on the product side. That's not as common. You might see that. What's a little more common is they'll actually provide the numerical value of the heat that's being released. But even then, that tends not to be seen as often as the enthalpy of reaction being written on the side. So typically you'll have your balance equation, and then they'll give you the value of your enthalpy of reaction for that particular reaction. Now, what you always have to pay attention to is if the sign is negative, it's telling you it's an exothermic process because the system is losing the heat. The heat is exiting, it's releasing it to the surroundings. So remember that sign tells you. So if delta H is positive, so your enthalpy is positive, it's the opposite. The heat is being absorbed by the system from the surroundings. So that's an endothermic process. So how would you see that? Well, again, they might write heat on the reactant side because the reactants require the energy to make the product. So the reactants absorb the heat. They might write the actual numerical quantity of heat that's required for the reaction. But again, more commonly, on the side, they'll write the enthalpy of the reaction, they'll write the value for that reaction, and then they'll show that it's a positive sign because it's endothermic. So why are we going over this? Well, the enthalpy change in a chemical reaction is going to be related to stoichiometry. So just like stoichiometry, where we can measure grams, convert it to moles, or if we're doing solution chemistry, we can measure liters, convert it to moles using molarity. We have to understand that the enthalpy change in a reaction is an extensive property. And what that means is it depends on the amount. So an example is if I'm burning wood, right, the more wood I burn, the more heat is released. So that's an example of a extensive property depending on the amount of fuel that is burned. An intensive property is independent of mass. So an example of that might be density. The density of water is 1 gram per milliliter. It doesn't matter if I have a liter or a hectoliter, the density is still 1 gram per mil. But with the enthalpies of change in chemical reactions, the more reactants you use, the more heat. So by convention, we can calculate the enthalpy change using mole ratios. So when I see this balanced reaction of the combustion of propane, I should know that that's propane because it's an alkane with 3 carbons. Well, I see that there's actually a mole ratio. Per 1 mole of propane that's burned, I release negative 2,044 kilojoules. Just like there's a mole ratio with the oxygen. Per 5 moles of oxygen reacting in this combustion reaction, it also yields the negative 2,044 kilojoules. Well, what if I actually burned 2 moles of propane? Well, then I would just take the enthalpy of this reaction, which again, this is per 1 mole. If I burn 2 moles, simply multiply it. So again, why are we going over enthalpies of reactions? Because they're very common with stoichiometric calculations. So we were just looking at the balanced combustion reaction for propane. So let's say a homeowner has a barbecue in a propane tank that's 13.2 kilograms, and they want to calculate the amount of heat in kilojoules associated with the combustion of their tank. Can we do that? Of course, stoichiometry. So we're given 13.2 kilograms, and we want to know the amount of really enthalpy of reaction, or Q at constant pressure. So how do we do that? Well, like our stoichiometric calculations, whatever unit you're given, convert to moles so we can get to that mole ratio. Okay, we were given kilograms of propane. Well, we can easily convert that to grams using the metric system. And then we can easily go from grams of propane to moles of propane like we've been doing using molar mass. But instead of converting the moles of propane to moles of, let's say, product like CO2 or water, we're actually using the mole ratio to convert it directly to the heat of the reaction. So we see that 1 mole is negative 2,044 kilojoules. Now the 13.2 kilograms is more than a mole, so we'll get more than 2,044 kilojoules. We'll get 6.12 times 10 to the 5th kilojoules. And we see the negative sign. You have to make sure you have that negative sign that's provided in the enthalpy of reaction to show the direction of the heat flow or the heat transfer. So this is showing that the heat is transferring from the system to the surroundings. Heat is being released. It's negative, it's exothermic. So the reaction is producing heat and the surroundings are getting warmed up as a result. We see that the units of kilograms cancel, grams from the molar mass, and moles, and I'm left with kilojoules. So I hope this video helps you understand how we can use enthalpy of reactions in stoichiometric calculations. If you guys have any questions, go ahead and leave them in the comment section, or you can email me directly. And thanks for watching.